Good morning and good afternoon, everyone. My name is Nicole Drake. I'm a Press and Marcom Specialist with MSC Software, and welcome to today's webinar titled Multiscale Analysis and of Composites from Chemistry to Part Performance. Our presenter for today's session will be Joe Sharp from e-Xstream Engineering, Dr. Andrea Browning from Schrodinger Material Science, and CJ from CMP.
Thank you, Nicole. Okay, so just a brief introduction for Andrea and myself. My name is Joe Sharp. I'm from e-Xstream Engineering, which is an MSC company. I'm a business development engineer there, and I started in 2016. Formerly, I was with the Boeing company for many years in many roles. The last one and most relevant was as a manager in their research and technology division of the computational methods group, which addressed advanced materials modeling and failure analysis. Andrea, could you tell the folks about yourself?
Sure. Thank you, Joe. So I am Andrea Browning. I'm with Schrodinger's Material Science Suite, and I am the project manager, principal scientist for the polymers area. I joined Schrodinger just this year, and prior to that, I was also at the Boeing company working on computational methods, including polymer modeling. And my background is in chemical engineering, and so these kind of models I've been doing for a number of years in a number of different places, and now at Schrodinger.
All right, thank you. So let's just jump in then. Okay, so we want to talk a little bit first about why we're even talking about this topic. So in an aerospace setting, this is what the materials development cycle looks like. So whenever you design an airplane and then you look at the next airplane, you always identify places in the previous design where, of course, you could look for improvements and performance improvements. And one of the big drivers for that is always in the materials area. So PD is always looking at places where materials can help them improve performance and make breakthroughs. Unfortunately, with the way that the material development cycle happens now, those ideas for improvements and those needs come out of that PD activity and go into a materials development activity, which is largely empirical. And there's R&D, there's formulation, there's scale-up, characterization. All of those things need to be done. And in several of the last large materials development programs, that has taken 8 to 10 years. And actually, so the actual materials development wasn't even finished during the program. And they had to do some things to alleviate the problems that were caused by that. So using analysis and simulation, we look to shrink that development and materials development cycle down to 2 to 3 years, which would be ideal, which would make it fit into this process in time for firm configuration and production material orders. So what does that look like exactly? I mean, how does this happen? So the requirements and the improvements flow back and forth from the airplane product platform, whether it's an aircraft or a spacecraft, and then back through the resin formulation that supports the laminate performance. But how do you link those things? Right now, it's all empirical and experience-based. You have some needs at the vehicle level, and then you have some ideas and some experienced and very smart people down at the formulation level and the structural team in the middle, and then you try to work it out. But simulation can link the requirements to the material formulation and architecture. If you can work that backwards and forwards, then you can have a more intelligent development process that pulls those things together and forms direct relationships between the chemistry and the performance that you need on the platform. Okay. So what do you need in order to do that? How does that work exactly? So you need to have a multi-scale analysis chain. You have to have one that works and passes the information from one level to the next, in a way that is physically consistent and predictive. So if you start from the molecular level, the chemistry level, you need to be able to pass information computed there up to the microstructure level to determine the lamina and laminate properties. You then have to relate the lamina level to the continuum level, so the part level, and then you have to be able to predictably simulate the response of the structure of the laminate itself. So any multiscale analysis chain can't have any gaps in that process. So you can't have a place where the linkage breaks down and you have inputs that are required that aren't predicted from molecular dynamics for the matrix. So what are those requirements? Like I said, the continuum failure theory that has to use properties that are computable from MD. Because if you have a failure theory or an approach that requires something else, some sort of testing in that space, then you can't do virtual formulation. You can't directly link chemistry to performance. You have some options. It can be concurrent or hierarchical. The approach that we're going to show you today is a hierarchical approach that computes properties at one level and passes them to the next to complete the chain. But you could also have a concurrent methodology where the continuum level could call down to, smaller levels of granularity. You have to have a consideration for model size and time span limits. So at the MD level, the time spans are very, very, very short, and the strain rates are very, very high. So you have to take that into consideration when you're building your analysis chain to make sure that you're not relying on properties that are sensitive to those things. And there are lots of materials properties that can be simulated. You can simulate static and dynamic structural response. You can also look at chemical, optical, and magnetic and electrical responses at the chemistry level and at the microstructure level. So what kind of failure theory links these things together? If you look at traditional failure theories in structural analysis, you'll find that nearly all of them, or all of the traditional and heavily used ones, are ply level analysis and assumptions where they look at the plies as homogeneous materials and then define a failure envelope around them using ply level failure testing. That can't be computed by MD. The only theory that's out there right now where the critical values can be MD calculated is called onset, and also known as SIFT, and it links the length scales. It assumes that deformation in the matrix drives material failure. And you have two allowed deformations. This theory is very old, so this goes back to von Mises, but your matrix can suffer dilatation and fail, or distortion and fail. And SIFT assumes that these things are characterized by the strain invariance of the strain tensor. And so I'm going to pass this over to Andrea right now, because she's going to tell you all about the MD protocol to calculate these things.
Thank you, Joe. Great. So the molecular dynamics is a technique that allows us to model the polymers at a molecular level. And with that molecular level modeling, what we can do is build a representative structure for the polymer material. What we're showing here is a thermoset resin. So you have a simple resin system with an epoxy and amine, and you can cross-link a collection of those monomers into a representative structure, and then you can interrogate the properties of that polymer system or that thermoset. And we can look at glass transition temperature by taking our representative polymer and looking at the density at different temperatures and projecting that from the lower and the high temperature regions to what the glass transition temperature will be. And so you can see with this particular protocol, we can run from higher temperatures, cool it down into lower temperatures, and get a glass transition temperature around the 450 Kelvin region. We can do that projection in different ways depending on the system, and we can look at what's going to be best for the particular polymer, and also look at different methods and can come to a conclusion on what the glass transition temperature is. We can also take our representative polymer and we can strain it. And so this is very similar to what you would do in an experiment, except we're doing it on the nanometer level. So you are pulling or pushing on the polymer in different directions and seeing what the response of that polymer is, or a thermoset in this case. And we can do that in a rate kind of manner. So we are straining successively, and so you get a curve like the one shown on this slide. You see a stress versus strain behavior, and we can pick out where the inflection point is. So we can look at the first inflection point and relate that to the yield. So we can see an elastic behavior of the polymer in the initial straining. So you see the straight line. If you look to the left of the plot, starting at zero strain, you see this kind of a straight line. So that's the elastic behavior, and it goes up and it begins to yield. In this case, around 5% yield. You can go to the next slide. As I mentioned, we have different ways of doing the fit for glass transition temperature. And what this allows us to do is really interrogate that behavior of the polymer, and we can compare the different methods, and if we don't see similar behavior between the two different methods, we can look in more detail at the results and see if there's a particular reason for that. If we find that one method for a particular polymer system works better, then we can use that. But overall, what we find across a wide range of polymers that we come very close to the experimental glass transition temperature with this method. So even though the glass transition temperature is a long time scale, can be a long time scale behavior, we can get a prediction for that property in our models at a nanometer size scale. And what's really powerful with the more present-day techniques and what we have with the Schrodinger software is that we can run very long times comparatively for these simulations. So we can do hundreds of nanoseconds, so we can get these kind of calculations very quickly with our GPU simulation techniques. Go to the next slide. And this is, again, talking about the uniaxial strain, shows it a little more closely. And so you can see that inflection point, and then we have a banded region for the yield, so you can look at where that inflection point is within the strain simulation. Let's go to the next slide. I think that's it. In conclusion about these molecular level simulations is that it allows you to look directly at what the effect of the chemistry is. So we can connect different monomers together, different polymer units together, cross-link them together. We can look at linear polymers. We can look at branch systems. We can look at networked polymers. And we can interrogate them for, as we showed on the other slides, for the thermomechanical properties, but we can also look at what might happen when you add in moisture. What might happen as you start to break bonds or as things start to age. And so what you can do is get the pristine polymer properties, look at how different ratios of the epoxy and the amine might affect your properties. And then you can start to also look at what might happen to your system as different things happen, like you get moisture ingress into your system. And this allows you to very quickly screen through different polymer systems, as well as understand how the polymer affects your properties overall, and what might be affecting your polymer properties. And I think that's it for me, Joe. Joe, are you on mute? I can't hear you.
I was muted. Okay, there we go. So revisiting the multiscale analysis chain. So when we looked at this before, we had some options for how to do it. I'm going to talk a little bit about how we would actually do this in practice. So the molecular dynamics piece that Andrea just described would compute the matrix, from chemistry would compute the matrix properties. So the things that we're talking about there are all of, you can tease out the modulus, the Poisson's ratio, the thermal properties, the TG, all of those things that are required to build up the composite microstructure and to deduce lamina properties can be computed for the matrix at the molecular dynamics level. Those things can also be computed at different conditions, as she said, like in the presence of moisture, in the presence of aerospace fluids, after aging at different temperatures. So you can investigate those properties at a number of different states, which are very, very difficult to test for empirically, and especially in the formulation phase. So this also reduces the risk of a development program if you know that you're sensitive to moisture, if you know that your formulation is weak at high temperatures, you can take steps to fix it. So the MD analysis is very powerful in giving us a view of how the matrix behaves at all of these different conditions. So those properties in this hierarchical structure, so those properties are fairly compact. The things that come out of MD, for example, represent just a handful of numbers that can then be handed over to the microstructure modeling piece, such as done in Digimat, where we can build up the structure from the geometry of the microstructure. So you do have to get fiber properties, but those are typically available from other systems. Those are, or very, very similar, fiber properties from one system to the next. So in a virtual formulation example, you can get enough fiber properties to do the microstructure modeling. So those properties come out of molecular dynamics. They're passed over to the microstructure modeling, which computes the lamina properties that are required for the part level analysis. So those lamina properties move over to the continuum FEA. So that, and I'll talk about dehomogenization in a second too. So the continuum FEA model will give the structural response of the laminate under load. So if you're looking at something like an open hole coupon, the lamina properties will tell you what the stress, will inform that model and tell you what the stress and strain distribution is inside that coupon. So that will give you the structural response. The microstructure model also gives you information telling you how to do dehomogenization when it comes time for failure. So composite laminates and composites in general are not materials. They're structural systems. And they fail as a combination. They fail as a combination of failures in the fiber and in the matrix and how those things work together. In order to accurately examine failure in a composite, you have to do dehomogenization at the failure step and look at the matrix and the fiber strains separately. If you assume a homogeneous material, you're going to miss a lot of things that are very important. The other thing about that too is that if you look at what the criteria are for failure for various platforms, composite aircraft, spacecraft, whatever, the customer's criteria for failure often isn't two-piece failure where the composite comes apart. They want to know when the matrix starts to fail, when you first start to get matrix failure, or when the first fiber breaks, or essentially when the first detrimental event happens inside the structure. Those things are important to them. So in order to examine those things, You have to dehomogenize the stress and strain inside the composite to look at failure. And so those things all go into the failure assessment. And what comes from molecular dynamics is the matrix failure critical properties, the onset critical invariance. Those things determine when the matrix fails. And so if you have a SIFT onset-based failure criteria and you're doing dehomogenization at that level, then you're able to accurately assess how the composite is performing and how it's failing and how all the parts are working together at that continuum part level, which completes the chain from chemistry to the part and allows you to look at a number of different conditions and examine your entire design space without doing a lot of empirical testing. Okay, there we go. So in summary, we can see how multi-scale analysis accelerates the composite, the innovation in composite materials. It allows the materials developer to look at their formulation across the entire range of the design space for all of the tests that are required from the customer. It allows the customer, for instance, an aerospace OEM, to look at and maybe reverse engineer some material properties that they would like to see that would be advantageous to their design. So they can formulate better requirements for the material suppliers and do a reverse engineering step. Those two things work together to accelerate innovation in materials. Linking the link scale requires that the continuum analysis only uses properties that are computable by molecular modeling. If you have any step in there that requires something that you can't get from the chemistry that isn't based on physics and thermodynamics, then the chain is broken. Only SIFT onset-based analysis at the continuum level currently meets this requirement. And multi-scale analysis also addresses, like we stated, the environmental effects and reduces program risk, time, and cost, because those things are all often tested at the very end of the program because of the requirement for conditioning, coupons, which takes so long to do. It can take months, weeks or even months to condition a coupon for moisture and temperature. So the multi-scale analysis is a very, very powerful tool for both material suppliers and aerospace OEMs in moving forward with materials innovation. And I'd like to thank you for listening today. If you have questions or comments, our emails, Andrea and myself, are on the screen. So with that, I would like to thank everybody for tuning in today. I would like to thank Andrea for co-presenting with me on all the hard parts. And okay, thank you for listening to our webinar today, and I think we'll be signing off. Thank you.